So a zener diode also has, because of the fact that it can hold a constant voltage, I can also use it in another application. So remember, let's go back to a full wave rectifier over here. And I did tell you that this is, yes, it is technically a DC signal, but it's not a very good one. Yeah, it's kind of a sucky signal to use. So what we can do is that we can put a RC circuit capacitor here to kind of smooth out the waveform, because by the time, okay, so it charges, discharges, charges, discharges, right? But before it can fully discharge, it's already changed direction. So it charges, but before it can fully charge, yeah, before it can fully charge, the signal changes direction again. So instead of going all the way down, all the way up, all the way down, it wants to go down, but then before it can go fully down, it charges up again, and then discharges, charges up again, discharges. So because of the capacitor here, uh, the signal doesn't go all the way down, doesn't go all the way up here, okay? So yes, it is starting to look somewhat like a nice DC signal, but it's still kind of choppy. So one way we can solve this is that we can put a zener resistor combination here. And if this voltage is going to be greater than my VZ, I know this fella is going to be held at VZ. And if this fella is going to be held at VZ, therefore, the load across, the voltage across the load is going to be held at VZ. So I get a very nice DC signal here just by putting my zener diode. Okay, so interesting how a zener diode can be used. Now I want you to try out worked example 7.6. Make sure you are able to get the answer. And pause the video now. After you work out 7.6, pause the video, try review question 7.7. And then once you're done, play the video again and let's see whether we are able to get the answers together. Okay, so pause the video now. Okay, so let's do our circuit analysis here. Yeah. Now VZ of 5.1 volts. So they want me to determine what is the voltage across RL when the DC supply is 6 volts and the DC supply is 12 volts. So let's start with a 6 volts first. Okay, so remember, I'm going to not consider this. I'm going to treat it like an open circuit, and I'm going to do what is the VL here. So part A, VL equals to 1000 over 1680 multiplied by 6 volts. And this will give me, let me pause. Okay, so 1000 over 1680 times 6 volts. This will give me 3.57 volts. Now 3.57 volts is less than my VZ, my zener voltage of 5.1. So if I were to draw one more time the IV characteristic, again, not concerned about when it's forward bias because we are looking at it from a reverse bias. This is my 5.1 zener voltage. We are operating at 3.57, which is somewhere here. And this is a no-go zone. We don't want anything below the zener voltage. So in this case, the voltage across VL, therefore, let me change it to green. The voltage across VL stays at 3.57 volts. Okay, so basically the zener diode is kind of useless there. It's not doing anything. But let's take a look at what happens when, let's use a different color for part B. Let's go for this nice dark blue. So part B, let's do part B here. What happens when this is now 12 volts? Okay, so same thing, doing the voltage divider method. VL equals to 1000 over 1680 multiplied by 12 volts, and this will give me 7.14 volts. Now this is greater than my zener voltage of 5.1. Therefore, if it's greater, VL will be held at 5.1 volts. Okay, so that's the answer for part B. If it's greater than VL, it will be held at the zener voltage of 5.1. Okay, so to calculate the power dissipated, remember power formula is IV. All right, so I have to go back to part A. Yeah, so to calculate the power dissipated in a zener diode, first of all, for part A, let me go back to green to differentiate. For part A, there is no power because there is no current through the zener diode. Okay, remember, this is acting as an open circuit. There is no current running through here, right? So that's part A. So let's go to part B. So part B, I first have to calculate what is my I value, my IZ. Okay, so step one, I have to calculate what is, let's call this I1, yeah? I1 is V over R, and the voltage across here is 12 minus 5.1, okay, 12 minus 5.1 over the resistance of 680. So this will give me 10.1 milliamperes. Okay, so this is 10.1 milliamperes. And I also need to find out what is the current over here. Let's call this IL. IL, same thing as V over R. V is 5.1 volts. Remember, it's held at 5.1 volts, the zener voltage. And here is 1000. This will be 0, 1, 2, 3, point 0, 5, 1. Okay, 1, 2, sorry. 0.0051. 1, 2, 3. Yep. Okay, amperes. Right? Wait a minute. Yep, which is 5.1 milliamperes. All right. So if 10.1 goes in here and 5.1 goes in here, therefore IZ is 10.1 minus 5.1, which is 5 milliamperes. Okay, so now I've got my IZ value, which is 5 milliamperes, and the voltage across the zener diode is 5.1 volts. I'll end up with 26 milliwatts. Okay, so that kind of concludes the chapter on diodes. I know it's a very big chapter. So consolidate your learning. The next lesson will be me asking you to do chapter 7 worksheet. After you're done with that, scan it, upload it, and I've supplied the link in your Google Classroom. Before you end, I've gotten ready 2 videos that I feel will help you learn about diodes more. My favorite YouTuber, Electro Boom, you can go and search for him making a full bridge rectifier. I'm sorry, I'm not as entertaining as he is, but it's quite an interesting video. And I found another video about another Aussie fella um, explaining what zener diodes are. He provides a greater in-depth circuit analysis. Maybe listening to an Aussie accent will help me understand it better. Okay, so thanks for watching. Thanks for watching this video on the chapter on diodes, and I'll see you next time on the next chapter.